So today we are going to be continuing our discussion of interconnection networks. And I wanted to say a few notes about interconnection networks in general. A lot of interconnection networks, or how do I put this? Interconnection networks can be very broad. So sometimes people talk about this as hooking together multiple computers, things like the internet, very wide scale interconnection networks. You could also think about it connecting things together in a very small place, for instance, on a chip or on-chip networks, and things in between. So for instance, computers where inside of one chassis, for instance, there's some interconnection network between different processors, or processors in memory, or I/O devices, processors in memory inside of one box, between multiple chassis, something like a supercomputer, or wide area networks. All these things broadly fall under what we're talking about here as interconnection networks. And I wanted to bring this up because someone came during office hours this last week and said, oh, you're talking about switches. And switches are, in my networking class, we learned about switches as this very well-defined thing. A switch is like an Ethernet switch. You plug some cables into it, and the definition of switching that we were using, the definition of switching that we were using in our lectures here were not the same as the definitions that were being used as a sort of Ethernet switch or Ethernet router. And that's true. So we're looking at a much broader class of networks here than just something like Ethernet or IP networks. We're looking at, we call them interconnection networks because it can be ways to connect things together. It does not have to be with a specific protocol. So just to recap, switching is the manner in which you connect different things together. Topology is the layout or the connection of the wires. Routing is the algorithm used to route packets across, or route packets or data, or if it's a circuit switch network, route calls across a network. And then we're going to look at flow control a bunch today, which is how do you actually prevent data from getting lost on a network. Just to recap, we talked about this last time. We have a message, which is made up of some number of bytes, we'll say, or some number of bits. From a nomenclature perspective, we can split this packet into we can split this message, into a packet here. And typically, you sort of have a head and a tail to a packet, and maybe there's a destination and a length is pretty useful in our header, and there may even be a tail bit. Sometimes some networks actually have bits or prologues that say the packet is being completed now. And inside of our packet can be made up of multiple flow control digits or flits. A flow control digit is the minimal amount of data which can be flow controlled upon a particular link, or the minimal amount of data which is accounted for, if you will. But that flit is not necessarily the smallest amount of data here. You can actually split that up into your flit, if you will, into multiple fits, where the fit is a physical transfer digit. And a good example of this is if you have a network where, let's say all of the data going across this network is always accounted for as 32-bit words. But the links on the network are only 8 bits wide. So a good example of this is you're trying to connect together two chips. You only had 8 wires to connect the 2 chips together. So you have 8 wires connecting those 2 chips together. It makes really no sense to try to flow control on any basis smaller than that word, because the smallest thing you're going to try to communicate is, let's say, a 32-bit word. So you're going to do all the flow controlling and all the accounting on the 32-bit flit, but inside of that, it'll be made up of 4 bytes or 4 pumps, or 4 data transfers across the actual physical wires. And that's a physical transfer digit. We talked about this last time. Circuit switching, store and forward, and cut through, or what's known as wormhole routing, or wormhole switching. Circuit switched is you physically run a wire between point A and point B, and you reserve that whole length the whole time. And there's typically what's called a call setup and a call teardown phase. Store and forward is that each router along the path will buffer the entire packet and wait till the end shows up before it starts to send ahead to the next router over. So it literally stores the whole packet and forwards it. And this is actually typically sort of our Ethernet routers, and our internet routers will typically try to do something like store and forward. If you don't care about latency, this makes a lot of things easier because you don't have to worry about some of the deadlock concerns that we'll see in a little bit with cut-through routing. Cut-through routing matters if you start to worry about latency. Cut-through routing, you're actually going to send the head onto the next router before you've received the tail of the message, or the tail of the packet. So you can actually worm through the network. So one packet will actually, could potentially go across multiple routers across the network, and one router will not have completed the packet until the next one has started. So to draw sort of an example of this, we have a packet here which is let's say 8 words long. And we have some sort of architecture where there's, let's say it's a ring or a one-directional torus. Looks something like this. And we're trying to send this packet. We inject the packet here. Each one of these are routers. So they have some sort of switching fabric inside of it. In this case, it's a 2-to-1 mux, which will take the input and the sort of flow-through case. And we inject here, and let's say this is destined for this output link here. We're actually going to use multiple of these links, or multiple of these routers and links at a time. So we start to send, let's say one here is the header. We'll start to send the header. And then the next cycle, we'll send the next word. And this can flow over here. And 1 can be here, and 2 can be there. The next cycle, 1 will be in this. Let's say there's a pipeline register somewhere along the route here. 1 will be here, 2 will be there, 3 will be there. And we're about to send 4. The next cycle, 1 has arrived, 2 is there, 3 is there, 4 is there, 5 is being sent. And it continues going on until finally 8 slowly moves across the network and goes out. So we call this cut-through or wormhole routing.